Picture this, an event so powerful that it spurs the birth of an entire universe. That event is none other than the Big Bang. The Big Bang, in the simplest of terms, is a cosmological model that explains where and how our universe began. The theory paints a picture of the universe bursting into existence from a singularity, a point of infinite density and temperature. Over billions of years, this initial explosion expanded and cooled to form the vast cosmos we know today. From a tiny singularity to the vast cosmos we know today, the Big Bang Theory paints a dramatic picture of our universe's origins. The Big Bang Theory didn't just materialize out of thin air, it's the product of centuries of scientific thought and observation. The term Big Bang was actually coined by British astronomer Fred Hoyle in the mid-20th century. But the roots of the theory extend much further back. In the early 20th century, a Belgian physicist named Georges Lemaitre proposed that the universe began as a single primeval atom, a concept that laid the groundwork for what we now know as the Big Bang Theory. Around the same time, American astronomer Edwin Hubble discovered that galaxies were moving away from each other, suggesting that the universe was expanding. This observation provided key evidence to support Lemaitre's theory. Over the subsequent decades, additional discoveries like cosmic microwave background radiation further bolstered the Big Bang Theory. With each scientific breakthrough, the Big Bang Theory grew more robust, shaping our understanding of the universe. The Big Bang Theory isn't just a story. Scientists have gathered substantial evidence to support this cosmological model. The two most persuasive pieces of evidence are the cosmic microwave background radiation and the abundance of light elements. Let's start with the cosmic microwave background radiation, or CMBR for short. This is a faint glow of radiation that permeates the entire cosmos, and it's a snapshot of the universe when it was just a baby, approximately 380,000 years old. The CMBR is the cooled remnant of the hot, dense state of the early universe, a whisper from the time when light first became free to travel across the cosmic expanse. When the universe cooled enough for protons and electrons to combine and form hydrogen, it suddenly became transparent to radiation. This freed the light, which has been traveling ever since, stretching and cooling as the universe expanded and cooled. The detection of the CMBR in the mid-20th century by Arno Penzias and Robert Wilson was a landmark confirmation of the Big Bang Theory. The second compelling piece of evidence is the abundance of light elements. The Big Bang Theory predicts the creation of hydrogen, helium, and traces of lithium in the early universe in proportions that match our observations remarkably well. After the Big Bang, the universe was a hot, dense sea of protons, neutrons, and electrons. As the universe cooled, these particles began to combine in a process known as nucleosynthesis. This process created the first light elements in the exact ratios that we observe today. These observations provide compelling evidence for the Big Bang, reinforcing its status as the leading theory of our universe's origins. They demonstrate that the universe we live in today evolved from a hot, dense state, and they allow us to peer back in time to the very beginnings of the cosmos. In the grand story of the universe, these pieces of evidence are crucial chapters underpinning our understanding of where we came from and how we got here. The Big Bang wasn't just a colossal explosion. It set the initial conditions for the universe as we know it. Let's travel back in time, nearly 14 billion years ago, to a moment before the universe existed. Picture an infinitesimally small point of infinite density and temperature. This is what scientists refer to as a singularity, a point where our understanding of physics breaks down, and it's the state from which our universe was born. Now, when we say the universe started as a singularity, we're not talking about a tiny dot in the middle of a vast void. No, the singularity was everything. It was all the matter, all the energy, and even all of space itself, compressed into one unimaginably dense point. From this singularity, the universe began to expand. Not an explosion in the typical sense, but an expansion of space itself. As it expanded, it also cooled. From this intensely hot and dense state, it cooled down enough for the fundamental forces of nature to separate. Gravity, electromagnetism, And the strong and weak nuclear forces which govern everything from the orbits of planets to the reactions in the heart of the sun all came into their own. This is also when matter, as we understand it, began to form. As the universe continued to cool and expand, particles of matter and antimatter began to take shape, setting the stage for the cosmos we see today. These initial conditions set the stage for the universe's evolution, shaping the cosmos we observe today. From a singularity to a sprawling cosmos, the timeline of the Big Bang is a journey through billions of years. Let's start our journey at the very beginning, at the moment of singularity. Here, all matter and energy of the universe was condensed into a single point. This was a state of infinite density and temperature, a moment where our current understanding of physics doesn't quite apply. Then, in a fraction of a second, the universe started to expand rapidly, faster than the speed of light. This period, known as inflation, saw the universe grow exponentially, from smaller than a proton to about the size of a grapefruit. Following inflation, the universe continued to expand but at a slower pace. The temperature fell, allowing particles to form. Quarks, the building blocks of protons and neutrons, started to come together. This epoch is often referred to as the quark soup era. About a microsecond after the Big Bang, the universe was cool enough for protons and neutrons to form. This was the starting point for nucleosynthesis, the process that led to the formation of the first light elements: hydrogen, helium, and traces of lithium. Fast forward to around 370,000 years post-Big Bang, and the universe had cooled down enough for atoms to form. This event, known as recombination, made the universe transparent for the first time, allowing light to travel freely. The light from this era is still observable today as the cosmic microwave background radiation. As the universe continued to expand and cool, matter started to clump together under the influence of gravity. Over hundreds of millions of years, these clumps grew into galaxies, stars, and eventually planets. This timeline gives us a glimpse into the past, providing a roadmap to the universe's evolution. The Big Bang Theory not only explains where we came from, but also sets the stage for understanding the universe's future. From the singularity to the cosmos we observe today, every step in the timeline brings us closer to understanding our cosmic origins. The universe holds many mysteries, and among them are two elusive entities: dark matter and dark energy. These cosmic phantoms, unseen but felt, make up a staggering 95% of the universe, leaving a mere 5% for all the stars, planets, and galaxies we can observe. Let's start with dark matter. It's called dark, not because it is some sinister force, but because it does not interact with light. We can't see it, but we know it's there because of the gravitational pull it exerts on galaxies. Without dark matter, the stars and galaxies would zip away like unanchored boats, rather than orbiting around the galactic center. Then there's dark energy, even more mysterious than its matter counterpart. Unlike dark matter, which pulls things together, dark energy pushes them apart. It's the force that's causing the universe to expand at an accelerating rate, a discovery that earned the 2011 Nobel Prize in Physics. Now, you might be wondering, how can we talk about something we can't see or touch? Well, that's the beauty of science. It allows us to probe the invisible, to understand the universe beyond our human senses. Dark matter and dark energy are vital to the cosmic structure. They're like the unseen scaffolding holding up a building. Dark matter helps galaxies form by pulling matter together, while dark energy drives the universe's expansion, creating the vast cosmic web we see today. To say we understand everything about these dark twins would be a cosmic overstatement. They remain two of the biggest mysteries in science. We're still trying to figure out what dark matter is made of, and why dark energy is causing the universe to expand faster and faster. But every mystery is an opportunity for discovery. As we continue to explore these cosmic enigmas, we may find answers to fundamental questions about the universe and our place in it. Despite their elusive nature, dark matter and dark energy play crucial roles in shaping the universe. In the aftermath of the Big Bang, the universe began to cook up its first elements. This was a time of extreme heat and density, perfect conditions for a process known as nucleosynthesis. In these early moments, the universe was a cosmic kitchen with protons and neutrons coming together to form the nuclei of the lightest and most abundant elements, hydrogen and helium. This was a delicate balance, a dance of particles under the influence of nuclear forces. As the universe cooled and expanded, the intense conditions required for nucleosynthesis ceased, leaving behind a universe filled with these light elements. But the story doesn't end there. The heavier elements that make up our world today, everything from carbon in our bodies to the silicon in our computers, were forged much later in the hearts of stars through stellar nucleosynthesis. This process of element formation is a testament to the universe's transformative power. The universe isn't static, it's expanding, a fact that's integral to the Big Bang theory. This idea of cosmic expansion is quite literally a mind-blowing concept. It's not about galaxies moving away from a central point, but rather the very fabric of space itself is expanding. The Big Bang didn't occur in a specific place in the universe, it happened everywhere at once. This is because, according to the theory, the universe started as a single point of extreme density known as a singularity and has been expanding ever since. Now, you might be wondering what's driving this expansion. Enter dark energy. This mysterious form of energy, which makes up about 70% of the universe, is believed to be the force behind the acceleration of cosmic expansion. Imagine a loaf of raisin bread dough in the oven. As it bakes, it expands, and the raisins, representing galaxies, move away from each other. But this isn't because they're propelling themselves away, it's because the dough, representing space itself, is expanding. The concept of an expanding universe helps us understand the Big Bang theory more deeply. It provides a dynamic picture of the cosmos, where the past, present, and future are interlinked through the lens of cosmic expansion. The universe's expansion is a key piece of the Big Bang puzzle, offering insight into the cosmos's past, present, and future. From a single point to a vast cosmos, the Big Bang theory has revolutionized our understanding of the universe. This remarkable theory has taken us on a journey through the very beginnings of time, space, and matter, shedding light on the origins and evolution of our cosmic home. We started by defining the Big Bang as a singular event that marked the birth of the universe, a moment when all matter, energy, space, and time sprung into existence from a state of singularity. From this initial condition of extreme density and heat, the universe began expanding and cooling, setting the stage for the story of cosmic evolution. We then delved into the historical development of the Big Bang theory, highlighting the seminal contributions of visionaries like Georges Lemaitre and Edwin Hubble. Their pioneering work paved the way for a new understanding of the universe, challenging prevailing cosmological paradigms and spearheading a revolution in thought. We explored the compelling evidence that supports the Big Bang theory, from the pervasive cosmic microwave background radiation, the afterglow of the Big Bang, to the abundance of light elements in the universe. These observational confirmations lend credence to the theory, reinforcing its standing in the scientific community. We ventured into the realm of the invisible, discussing the mysterious dark matter and dark energy that pervade the cosmos. These elusive entities play a crucial role in the universe's evolution, influencing its structure and driving its accelerated expansion. We recounted the chronicle of element formation, from the creation of the first light elements in the searing heat of the early universe to the synthesis of heavier elements in the hearts of stars. This process, known as nucleosynthesis, has resulted in the diverse chemical composition of the cosmos we observe today. We also addressed the ongoing expansion of the universe, a phenomenon first identified by Hubble and now attributed to the influence of dark energy. This cosmic expansion shapes the structure and destiny of the universe, leading us to ponder the eventual fate of the cosmos. Finally, we broached the intriguing concept of the multiverse and its implications for the Big Bang theory. This hypothesis, though speculative, offers a tantalizing perspective on the nature of reality, suggesting that our universe may be just one among many. The Big Bang theory has given us a window into the cosmos, illuminating our place in the universe. It's a testament to human curiosity and the power of scientific inquiry, reminding us that there's always more to learn, more to explore, and more to discover. So, remember to like, subscribe, and share to dive deeper into the wonders of science.